Well, thank you guys for having me. Appreciate it. Again, my name is Hoylman, and I am a research professor at the University of Montana in the climate office, and I'm also your assistant state climatologist for Montana. And before I get started, well, first I'll go ahead and say, today I'm going to be talking about drought assessment, super short. I just want to give you guys an idea of how drought assessment is done in this state because it's super important. Climate change and future risk for the Bitterroot watershed is what I'm going to be focusing on. So let's see if I can advance. Okay, cool. So who am I? I am a researcher at the university. I do a lot of work on hydrology and ecology. I did my PhD on a tributary of the Blackfoot, really looking at how water moves through watersheds and interacts with vegetation, trees, to basically cause differences in vulnerability and sensitivity to climate and climate change. Then I scaled that to the Western United States using a bunch of remotely sensed information from satellites. And I do a lot of work with groundwater up in headwater basins. So we go and hike around with groundwater drills. We break them down into backpacks effectively and then build scaffolding and drill cores into kind of remote mountain watersheds to understand what groundwater is doing out in these areas. It's really undefined. My PhD did a lot of work with endocrinology, a lot of tree ring work, and then, like I said, remote sensing using things like LiDAR, which is literally using radar from satellites and airplanes to measure forests as a whole, which is really cool. And as you can tell, I'm definitely a fisherman. That's like my main hobby, that, hunting, and backcountry skiing, and floating. So the Bitterroot is obviously something that's really special to me. The tributaries and the backpacking up in the Bitterroot is something I've done for a long time. And the fishery here is something that means a lot to me. And it's something that I'm actually personally very concerned about. As you can see, I like to go to a whole bunch of different places, Alaska, and go fish tarpon. I'm about to do that actually in a few days, which I'm super excited about. So going all over the place. So that's a little bit about who I am and what I do professionally. So today I'm going to be talking about a couple of different things. Like I said, first off, we're going to be talking about current drought conditions. I just want to give you guys an update on where we're at and kind of give you an idea of our process for drought assessment across Montana. And actually, to make sure I don't go too long, I'm going to go ahead and give myself a stopwatch. And then we're going to go on and talk a little bit about historical trends in precipitation and temperature for the Bitterroot specifically. So we're going to be talking about either Ravalli County or the Bitterroot watershed. These are going to be observed trends. And then we're going to start talking about snowpack in a couple of different ways, changes in our snowpack that we've observed historically, and future projections of those changes. So we're going to be definitely talking about climate change. And then I'm going to give you some final thoughts that kind of wrap it all together. So to begin, I was asked to give a presentation today on, precipitation, temperature, changes in those things, climate change, snowpack, implications for snowpack and the Bitterroot. But I think to start, I really wanted to just give you guys an idea of how drought is assessed across Montana, and then we'll go into those trends. Because of course, right now, we are definitely in a drought. And to give you an idea of how this works, and to give you an idea of the importance of drought assessment in Montana, drought assessment in Montana is responsible for literally hundreds of millions of dollars in disaster relief aid across the state almost annually. It depends on how bad the drought year is, but it's a huge economic engine for pumping federal economics into our state to basically persist through periods of dryness. And there's 4 of us authors in Montana that are responsible for drought assessment. We're spread across many different agencies, DNRC, NOAA, DNRC, and the actual, the state library, as well as the Montana Climate Office, which is where I work. And just to give you an idea, every week we do a huge kind of data assimilation process where we take tons of different data sets. I'm going to show you some of those in an interactive platform that we actually made in the Montana Climate Office, which is the authoritative source for drought information across the state. It was actually codified into the new drought management plan that dropped last year. And fun fact, we hadn't updated our drought management plan since 1995. And there's actually quite a bit of it in focused around fisheries and recreation. So the new drought management plan is really cool. And so every week we do this huge assessment. And basically we go on Monday morning, I get into my office and I look at lot of different data sets, everything from groundwater data to precipitation data, soil moisture, vegetation response from satellite imagery, stuff like that. And I put together all of that data into an assessment that says, okay, this is where drought's occurring, this is maybe where it's not. We send it out to a big listserv on Tuesday to a whole bunch of different people. I get a bunch of feedback, especially from people that disagree with me, because that's good, because this state is very, very complex, as we all know. And then on Wednesday, effectively, all of that information gets put together into a map, we package it off and send it to this thing called the US Drought Monitor. And the US Drought Monitor is out of Nebraska, Lincoln. It's part of the National Drought Mitigation Center, and it is responsible for triggering all of these relief efforts. So it's a super, super important process that, again, is responsible for hundreds of millions of dollars coming into this state. One thing that is not well represented in that drought assessment process is recreation industry and the outfitting industry. We try our best to reach out to outfitters to get an idea of ecological impacts of drought on the Bitterroot River system. The Big Hole, of course, has been a really big focus the last several years. And so I'm going to give you guys an idea of how to, if you're interested and want to be a part of this process, show you how to give me feedback during my drought assessments. So really quickly, I just want to show you kind of how this process works and just give you an idea of how we got to where we are today. So right now what I'm showing you is a precipitation anomaly grid. So this is basically using a bunch of different data. So this is using precipitation estimates across the entire state, and it's put into a framework called the Standardized Precipitation Index, which is SPI. And basically what it shows is just anomalies. And this is the backbone of how we do our drought assessments. We don't just use precipitation, we use many different metrics. But I just want to give you an idea of what these data sets look like, because it'll show you how we got to where we are today. So right now I'm showing you 120-day SPI for today, or 2 days ago. And what you can see is that the Bitterroot, right, which is here, I can overlay the watersheds to give you an idea, but you all know where we are, of course. But the Bitterroot watershed here, I'll zoom in, is experiencing a pretty significant deficit of precipitation over the last 4 months or so. And that's continued over the last 3 months, of course, as we get closer to today. 2 months, there's less of an anomaly. As we all know, February was much wetter than the rest of these last several months. And what that's resulted in, of course, is a reduction in our snowpack. So we have a bunch of different ways to measure snowpack across the watersheds. This is loading, but this is what snowpack looks like right now. So we can see there's a big deficit of snowpack, especially on the eastern portions of the watershed. And then we've actually done quite a bit better in the kind of main face of the Bitterroot here over the last several storms, and I'll show you some data that shows that. We also, of course, use a bunch of other types of information, like groundwater information. This is really cool. This is actually using information from 2 satellites that literally measure the gravitational pull of the Earth, and differences in the amount of groundwater actually pulls on a satellite and allows you to quantify how much groundwater there is. And what you can see is that our groundwater situation right now in the Bitterroot is not looking super good. We've been in a several-year drought, right? It's been about 3 years of drought conditions across western Montana, and that's resulted in some pretty big deficits. So where do we sit today? Well, I just want to show you how the drought monitor has changed over the last several weeks. So we're going back to January 9th. This is pretty early in the winter season. And effectively, over the last several weeks, this will load, we've increased the amount of drought across the watershed. So this is D2, or severe drought conditions, which is basically the triggering point for a lot of these relief efforts. So in the Bitterroot and all the way up to today, the Bitterroot is not doing super hot, and well, it is hot, but it's not doing super good in terms of the amount of water that's around. But places like the Blackfoot River Basin, the Middle Fork of the Flathead, the South Fork of the Flathead, the Swan are actually in worse conditions. So the Bitterroot is not doing as bad as other places, but it's not doing great. So that's where we kind of stand in terms of our drought conditions for today. And it's really a snowpack story right now, of course. So with that in mind, that kind of sets up the rest of my presentation. I'm going to be talking about changes in what we've observed over the last several years in terms of precipitation and temperature. And just wanted to put that context of where we are sitting in terms of drought conditions today, because I think it's really important and it's obviously on everyone's mind. So how has climate changed over the last 40 years? This is something that we can actually assess using information that we've observed. So we're using modeled information, and this is one of the kind of core products that the Climate Office provides, which allows you to basically click on a certain place. So like this is Ravalli County, and we can see over here, this is a precipitation time series over time. And we can see, of course, 1980 to 2020, precipitation hasn't really changed. This is something that we see pretty ubiquitously across the state. Climate change in terms of annual precipitation isn't causing a huge effect. What it is doing is shifting when precipitation tends to be occurring. We actually are seeing more precipitation during the winter and spring, but less during the summer. And for fisheries, that has kind of a two-sided effect, of course, because if we see more precipitation during the winter, as long as it's cold enough, then we might expect to see a little bit more of snowpack, which might cause a little bit more stream flow. But if we have less seasonal rains in the summer, that means that we might have lower flow conditions during the summer. So how has temperature changed? Well, I'm sure we're all sick of looking at plots like this, but this is for Ravalli County specifically, so the Bitterroot watershed as a whole generally, because the two kind of align. And what you can see is on the left, same kind of idea over time, so these are multiple years over time, and we have minimum temperature on the left and maximum temperature on the right. So you can see since 1980, we have had a significant, statistically significant and strong change in our minimum and maximum annual temperature over time. In general, of course, we've gone from about 26 degrees being our minimum average temperature to almost 30 degrees. That's a huge difference, especially when we're talking about snowpack. So what does this mean for snowpack? Well, this is a paper that came out recently by a gentleman, Phil Mote, who's one of the kind of leading experts on snowpack dynamics. It came out in one of the nature journals. And what it's showing you is basically April 1st sweep trends over a really long time period. So this is 1955 to 2016. Anywhere on this map on the left, I don't want you to focus on this yet, anywhere over here represents a snow-till site. And if we're all familiar with snow-till sites, they're snowpack monitoring sites that are at the highest of elevations typically. We have, I think, 6 in, the Bitterroot or so. Lola Pass, 12 Mile Creek, Twin Creek, Saddle Mountain, there's several. And we're gonna look at some of the data from these specific places. But anywhere where you see a red circle represents a location where we've had a statistically significant decline in April 1st SWE over that time period. So what that means is that we may be getting the same amount of snow, but the snow season might be shrinking, so we might have earlier melts, or we might be seeing less precipitation in general. But as you can see across the west, pretty ubiquitously, we're seeing a reduction in snow water equivalent, which is sweet. That's the amount of water that's in the snowpack. I should have said that earlier. So these are just point observations. We can also use snow models. So this is a model called the VIC model, which is the variable infiltration capacity model. It's just a fancy model that allows us to actually measure snowpack or model snowpack across space. And what you can see is that in general, these pictures kind of align. There's a lot of red on this map, which represents not good. But if you zoom in with a really pixelated image to the Bitterroot watershed, you can see that things are kind of different. It's not just ubiquitously red across the Bitterroot. And that's interesting for several reasons. So let's actually look at some of the data. And this is just data that I whipped up this morning from some of the snow-till sites. And what I'm going to do is just walk you through this. Again, on these axes here, this guy, this is over time. So this is snow water equivalent at the Twins Lake snow-till. So this is kind of like, this is west side of the Bitterroot, pretty high elevation. I think it's like 7,400 feet, and it's relatively south. So it's one of our higher elevation snow-till sites. And what you can see is, in general, there is a very subtle trend towards less snow during April 1st, but it's not statistically significant, which means that there's not a whole lot of evidence that at this site, snowpack is really changing that much over time. That's a good thing. We like that. We don't want to see reductions in snowpack. Over here, I'm showing the relationship for that site, the snow-till site of Twin Lakes, to mean flow between April and October for the Darby gauge on the Bitterroot. So what you can see is that there's a pretty strong relationship between the amount of snowpack that we get and the amount of flow that we get through the Darby gauge, which makes sense. I think we all would expect that, right? But what that means is that our snowpack and changes to our snowpack are really important for our flow states within the Bitterroot watershed, which probably isn't surprising. But this flow state over here is, of course, between April and October. What about late season flows? We're less worried about, spring flows. And what we see here is late season flows. There's a much less strong relationship between the amount of snowpack that we get and the amount of flow that occurs during August and September. So what that means is that flow during these later seasons is way less impacted by snowpack. It's much more impacted by groundwater dynamics, like that map I showed you that Grace was measuring. So that's not a good indicator, but also seasonal rains. Things like, of course, precipitation events that occur in August and July are really important for sustaining our base flows later in the season. But of course, it's really a groundwater story, and that's something that occurs over really long time periods. So that Grace data that was showing a lot of red, the groundwater data being really, really red, is a representation of that 3 years of drought. So our late season flows this year might be on the lower side, I would suspect. I'm just going to show you a couple more of these types of plots just to show you. This is 12 Mile Creek, so this is just a little bit lower down. The snow-till site's a little bit lower down than the previous snow-till site, but still at the Darby gauge. Here, we can actually see that there is a slightly better relationship, but not much. So again, over time, SWE at this site isn't really changing, but there's a really strong relationship between the amount of snow that we get and the amount of flow that we get. So that's important. But again, the relationship for when we're talking about late season flow is not that strong. So snowpack, what I'm trying to build this story is that snowpack is not really a good determination of our late season flows. So even though we like to conflate the two, I do it myself. I think about snowpack, oh, it's a bad year. That means things are going to be really bad in the late summer. Not necessarily the case. It's more about these groundwater dynamics, which are more longer term drought. A few more representations. This is the Saddle Mountain snow-till site. So this is more on like the West Fork. It's like, on the East Fork. It's like right on the ridge of the East Fork. There's a really, really strong relationship between these two, snowpack and flow in this location, but not, again, during late summer flow. And one more kind of a relationship. This is the Bitterroot site for Daly Creek snow-till, which is kind of like over by kind of Scalpahoe area, and then the Bell crossing gauge. And of course, there's much less of a relationship here because we use a lot of water for irrigation between that section between Darby and Bell. So there's less of a climatological relationship. Okay, so I'm just gonna skip through that. So the main takeaways here are that there's not really strong trends in snow water equivalent across the Bitterroot, as we've seen across the historical record, so the last like 40, 50 years, which is a good thing. We like to see that because as we saw from the previous slide with all those red circles, the Western United States as a whole is seeing a huge decline in SWE. But the Bitterroot is actually a little bit of like a pocket of not a huge amount of change, which is really good for us. Snow-till provides a really good indication of stream flow. We saw that from these really strong relationships. And it's more predictive for mean flow rather than late flow. And that means that it's really more predictive of like, of course, the amount of spring runoff that we get as opposed to late season kind of base flow conditions. But temperature is increasing. And we saw that in that previous plot. It increased from about 26 degrees minimum temperatures to about 30 degrees temperatures. So how is it possible that our SWE isn't changing, right? That's kind of a weird thing. And the reason behind it is because snow-till sites are at really high elevation. So this is a really important thing to remember when we're looking at data sets, especially those maps, those NRCS maps that show basin-wide conditions. And I'll show you one in a second that you'll be like, oh yeah, I know what you're talking about. They're at really high elevations. What that means is these sites that are at high elevations are buffered from climate change because changes in snowpack are of course related to basically exceeding that 32-degree mark, because it's not like a linear relationship, it's much more of a threshold. You have to exceed 32 degrees to have some impact on melt dynamics, or perhaps as transition from rain to snow. We all know it when we look out at the Bitterroots or you look out at the foothills, you can see that snow line, right? It's not a gradient, it's a line. And so as that temperature is marching up and getting warmer, it's slowly marching up the mountainside. So those highest of elevations are the ones that are going to be the last to respond to climate change. And why is this important? Well, because of this idea that I think of is called hypsometry, and this is an idea in geography. And all this means is that even though at low elevations we have relatively shallow snowpacks, there's way more area at those low elevations than there is at higher elevations. At high elevations, there's really deep snowpacks, but there's not much area. And that's what this plot basically shows, is that as you go up in elevation, there's a huge amount of area at these mid to low elevations. And then as you hit high elevations, the peaks, right, the tippy tops of the mountains, there's not that much area. So we really care about what's happening at these mid to low elevations because A, they're sensitive to changes in temperature over time, and B, even though they're not a super deep snowpack, they represent a really large volume of water. So why does this matter? Let's go back to 2021. I just pulled a Smith permit for July 1st. Sweet. I'm gonna be on the raft, flip-flops, slinging golden stones, like it's gonna be awesome. This is gonna be sweet. April 1st. I'm looking at snowpack in the Smith, 100% of normal. Sweet. I nerded out, did all the statistics on the flow. I was like, this is gonna be perfect. I pulled the perfect time. It's gonna be sweet. Well, go to 2021, and if we use information about snow across the entire basin, not just the highest of elevations, but you can see these snowpack measurements from SNOTEL, which I'm not bashing on SNOTEL. SNOTEL is an incredible tool. We need it. It's very, very good, but it is an incomplete picture. And what you can see is that along these highest of elevations, right, that's where we're not seeing huge reductions in snow water equivalent. Of course, this is an anomaly, so red is less than normal. So what you can see is that there's this huge amount of volume of water across the Smith watershed that was not being represented by the SNOTEL data, which if you account for all, this is the same time period, April 1st, 2021. NRCS suggests 100% of normal. These modeled snowpacks represent about 59% of normal. So you can imagine that might have a huge implication for what kind of flow regimes you might expect and the kind of water management decisions we might make depending on this perspective. Are we at 100% of normal or 60% of normal? So what happened? Well, of course, Smith River, this is the Smith River gauge. Here's the minimum recommended discharge for rafts. Of course, July 1st, I'm here. Boom. Record low flows, right? Yet we had 100% of normal snow, but not across the entire basin, just at those highest of elevations. So I just want you all, because we all have this kind of, you see it on all the fishing reports. All the fishing shops are showing these types of plots, these NRCS plots. Yeah, we're doing good. We're at 100% of normal. Just make sure, if you can drive up, I'm a backcountry skier, if you can drive up to St. Mary's to 7,000 feet and go ski, you're still hiking in boots to get to snow, that's like not a good thing. And it's a whole different picture because there's a lot of snow that's missing. So this plot here kind of shows it. So this is I was saying it's hypsometry, is that idea of the elevation to area profile. I'm a nerd, so I call it hypsoma-SWE because it's like the distribution of SWE across that elevation profile. And this red represents the amount of snow that should be on the ground based on the mean climatology, and the blue represented what it was at that day. So you can see up here where the SNOTELs were, they're not wrong. It is at 100% of normal. It looks exactly as it should. You can see this difference here is a huge amount of volume of water that we're missing that's at mid to low elevation. So that's one of these really strong impacts of snow snow change as a function of climate change that we should expect across the Bitterroot Valley. So, what does this look like today? Well, this is actually using that same model, the Snowpack model, instead of just looking at trends in snowwater equivalent at each of the SNOTEL sites. Now we can use that same model, but do it for every pixel, so across the entire distribution. And now we can see this is the slope of that relationship. So reds mean less snow over the last 20 years. Blue means more snow over the last 20 years. So what you can see is actually, as our climate change predictions have been suggesting, we're actually starting to see a little bit more SWE at these high elevations. And that's because we're seeing more precipitation occurring during the wintertime. But in places like the lower elevations of the West Fork, lower elevations of the East Fork, around the Scalcahoe zone, these are areas where we're starting to see changes in snowpack and reductions in snowpack, that loss of snow at that mid to low elevation. So this is going to be an important consideration as we move forward. So where do we sit today? Let me just make sure I'm doing it. Where are we going to sit today? Well, we were in really dire straits. Like I said, January 1st, this is where I showed you that first kind of drought map, and then things were bad, and we were kind of tracking this really low line. This green line is where we should be, and this is using data across the entire basin, so not just the SNOTEL sites. It looks the same as those SNOTEL plots, but it's using the whole basin map. And what you can see is that we've made some huge improvements this year, which is great, but we're still relatively low, but we're at about, I think the estimate's 87% of normal sitting today. So we're nowhere near as bad as we were, but we're still missing snow. And where are we missing that snow? In those mid to low elevations, like we would expect to see given this kind of climate change signature. So all this information is available on a daily basis on that drought dashboard. And you can see, you can just click on the basin and get these types of informatics every day. They're updated every day. Okay, so main takeaways. Basin accumulation varies, snow accumulation varies significantly across basins and as a function of elevation, aspect, all of the things that we know. And networks such as SNOTEL are really important. Again, I'm not bashing on NRCS. They are critical, fundamental data sets that we rely on really heavily, but they're not the whole picture. They lack the ability to describe this whole distribution of snow, which is critical for water resource management. We're not just worried about whether we got 10 feet at Lolo Pass or if we got 11 feet at Lolo Pass. We're worried about the entire watershed's water conditions, right, and volumetric storage. And despite this high elevation snowpack, despite this, our high elevation snowpack is declining somewhat in certain areas. Okay, so where are we headed? Well, I work at the Climate Office, so I would be amiss not to talk at least a little bit about climate change and climate change projections. But what's really cool is that in the Climate Office, we've been doing a lot of work with a NASA product that allows us to downscale climate projections to watershed scales. So all of the projections, except for the first slide that I'm going to show you, are based on only data for the Ravalli County or the Bitterroot watershed. So how do we do this? Well, there's a whole lot of nerds like me that sit at computers with cigarettes and type away, right? And just do a bunch of mumbo jumbo on our computers. And we use really, really big computers to do these climate projections because they're really, really hard to do. Why are they hard to do? Because we use this system and this method called the Navier-Stokes equation. If you're a nerd, this is a third order partial differential equation that occurs in all three dimensions, laterally and vertically. So what we do is we break the Earth into a bunch of different grid cells, and we basically perturbate based on different emission scenarios or et cetera, to basically try to see how the whole system's basically fluid dynamics change as a function of greenhouse gas emissions or temperature relationships to like snowpack, et cetera. And they're really, really computationally intensive. So you need, nerds, and then nerds to kind of analyze it. So how do we know that they work? This is a question that I get all the time, is how do we know that climate projections are even not just like, okay, Zach, yeah, sure, you could have just typed something up on your computer and here are some plots and whatever, I don't know what you're talking about. what we do is this concept of hindcasting. So what we do is we actually use these models, we run them from the past, the deep past, back from 1850, all the way through to 2021, or 2020, and use basically our observed changes, and the models have to be able to predict what has occurred to be able to be included in our global climate change projections. So there is predictive skill. There's a lot of uncertainty. Yes, there's a ton of uncertainty in these models, but they've been able to recreate past conditions, which is why we know that they at least have some information to give, right? And so what we do is there's a whole lot of different agencies. There's a whole list of them here. And this is from the CMIP 6 data. So this is the new global climate change projections that came out like 2 years ago. There's a whole bunch of agencies from a bunch of different countries and a bunch of different enterprises, and they all make a bunch of predictions, and then we use this whole envelope of predictions to make an idea of what's the mean, the average conditions that we might expect, which is that red line, and then the black line represents what actually happened. So does it match perfectly? No, it doesn't. And the reason for that is it's not trying to predict actual weather patterns. It's just trying to predict kind of climate dynamics, which are two different things. So this is how we know that our climate change predictions actually have some information. So where are we going? Well, it's obviously dependent on our emission scenarios. You might be familiar with the previous way of talking about emission scenarios, which was, I can't even remember the acronym anymore. Now we have this thing called SSP. It's a shared socioeconomic pathway. It just means basically like, there's a whole lot of decisions that we can make as a society. We could try to limit methane emissions. We could accelerate our carbon emissions. We could do this or that, right? There's a whole suite of ways that we could go. And kind of unfortunately, where we're sitting right now is right in between these the orange and red. That's kind of the trajectory that we're moving. So those are the projections that I'm going to be showing you. If we do a lot to cut our emissions, of course things are going to get better, but that's just not where we are. I drove my truck here. I drive to go fishing. Like, I am part of the problem, right? It's the way it is. So this is for Ravalli County. So this is data specifically from Ravalli County. Again, remember, we were looking at these data here. This is minimum temperature and maximum temperature. We already saw this increase using observed data. So we know that this tracks with what I showed you at the beginning of the presentation. And where are we going? In a not good direction. So what that means is that our water resources are going to change, and the dynamics of snowpack are going to change, and that line of impact is going to creep up and up and up the mountain. So it might take a decade or two to hit those snowtell sites, but as they move up, we need to be thinking about the whole watershed and the whole water dynamics of the entire basin when we're talking about water resource allocations and decisions. What about days above 90? This one freaks me out big time because, like, you know, you look at these and it's like, okay, minimum temperature is going from, and these are deviations from normal, deviations from now, 0 being kind of average conditions today. So we're talking about, you know, by 2075, 5 degrees warmer than normal than today. But the days above 90 is like what really means something to us, right? Like we've all sat on the boat, yeah?
That's Fahrenheit or Celsius?
That is in Fahrenheit. Oh, sorry. This is days above 90 Fahrenheit, but these are days. Yeah. So what you can see is that like we've all sat on a boat on the Mo when it's like 1,000 degrees and it just sucks. Like this is where we're going, which is no bueno, but it is what it is. Freeze-free days, again, going off the chart. Precipitation. Like I said, we didn't really see much of a trend. Again, the projections don't show much of a trend. We actually don't see much of a trend going into the future. If anything, what we see is an increase in variability, which means we should have more expectations of really low years and really wet years, which is really what we've been seeing. I mean, I would argue in general, like we go from boom and bust. It's just back and forth, and then dry days. So this is kind of me wrapping up. What does this mean for snowpack? Well, there's a really interesting paper that came out by Ben Lipna that kind of puts this into a theoretical framework of like, we don't know what changes in snowpack really means for our stream flow. And that's because a lot of the research that's been done has been using those high elevation snowpack data sets, those SNOTEL data sets, right? To project what's gonna happen in the future. But you can imagine this is now, right? And we have some predictive relationship between this site and there. But if we're not really accounting for all of this that's missing in a future scenario, right? And so as we move forward, there's a lot of research that needs to be done to basically take this like watershed scale perspective and think about what it means for water resources. And this is stuff that I'm doing with some of my grad students right now and working in the groundwater component as well, because that's obviously a really key piece of this story. So to find some final thoughts, temperature is increasing and expected to keep increasing over time. I think we all have observed that in our lifetime, and we should continue to expect that. So we need to make, any kinds of mitigation efforts that we can to limit that. Low elevation snowpack is expected to be impacted first, but represents a big volume because of that kind of hypsometric relationship, the area relationship of elevation. Future stream flow will be more reliant on seasonal rains in the future, and groundwater dynamics, of course. And then future seasonal rain dynamics are expected to become more and more variable over time. Stream temperature is also a huge concern. This is something that we're working on as well, making these projections of future stream temperatures, because of course we know that has huge ecological implications, especially for macroinvertebrates. So this is a lot of kind of depressing stuff at the end of this presentation. But what I'd like to end on these kinds of presentations with is Montana is a headwater state, and we all recognize that. You've heard it a million times, right? We drain the Columbia, we drain the Mississippi, Missouri, and we drain into Saskatchewan at Triple Divide. What that means is that we are in a very unique situation. The Bitterroot is a closed basin effectively, and so the watershed decisions, the water management decisions that we make here are going to impact us directly. Imagine if you're in Nebraska and things are changing. You have to deal with all the Nimrods upstream making decisions, right? I'm not saying anyone in any of those states are Nimrods. I'm just saying all the decisions that are made to better those folks might not be taking into account what happens downstream. And that means that their kind of decision power is rather limited compared to us. We can make decisions now that actually buffer our risk to climate change, and they will affect us. They will affect our kids, which gives us huge power. And that's a really cool thing. So even though we're not going in the best direction, we have an opportunity as a community to actually impact our own watersheds, which is unique. And it's something that we should not take for granted. And it's something that we should really try to hold up as power, because it's a really cool thing. So with that, there's a couple of links for some data sets, etc. And thanks again. Sorry for all the
questions? Yeah, sure. Go ahead, Dan. Okay, thank you for all that information. I'm going to do one question right now for you before we move on to the panel, and I want to remind all of you out there to please submit your questions. There's 50 of you here, and I've got 16 questions. So while we're doing this little transition, feel free to take out your phone. You are allowed to, in this situation, we encourage it. Take out your phone, enter a couple of questions before we move forward. So I'll take one for you now, Zach. You mentioned at the end that we have this incredible power to take action. Do you happen to have an example or two, one example of what communities are doing in the face of these changing dynamics?
Yeah. So one paper that we actually just published a month or two ago is looking at the impact of irrigation on stream flow dynamics. And in many places, like the Snake River Basin, the Colorado, the many of these big basins, especially in the Southwest and more arid regions, irrigation is literally withdrawing water from the stream via either groundwater, because groundwater and surface water are interchangeably linked. They are not separate, even though our laws might tell us they are not. And in many of these areas, taking water out of the groundwater or taking water out of the stream directly impacts the stream in a negative way. But there are actually places, especially like the Yellowstone Basin, where increases in irrigation over time have actually increased base flow. And you're like, how is that possible? Well, there's this thing called the irrigation efficiency paradox, where effectively across the United States, we've been kind of like pushed to adopt high efficiency systems like center pivot irrigation. And what that means is that we're putting less water on the landscape, and the plants are able to use it in a more effective, efficient way. But efficiency doesn't necessarily mean hydrologically good. And so in Yellowstone, there's actually been a huge, most people just use flood irrigation. And so what we're doing is literally taking, you can imagine a stream hydrograph when we're like, it's all muddy in May, right? Taking that water out of the stream that's just pumping downstream, pushing it into those irrigated lands, and all of a sudden now you're starting to increase your groundwater recharge, which is coming back with cold water later in the season, and actually increasing base flow later in the season. So that's like an example of a synergistic kind of response between agriculture, which may be seen as like a negative, especially when we're talking about ecological systems and fluvial systems like rivers, where there's actually some synergies there. And so there's many examples that are kind of like that, but that's one that I thought was really interesting as a way that we could both increase our amount of irrigation and potentially agriculture while still kind of providing an ecological service downstream later in the season when we really need that cold water in the system. So that's just one example, but there's many others. So thanks.